Hello everyone, today we're going to be doing exam 2 for transport 2, which will be covering convective mass transfer. Let's start with the problem. Right here we have a cylindrical pipe. It is full circle inside, and it has liquid running down the inner surface of it. It doesn't go across the whole thing, just the inner surface. It goes in on the top, out at the bottom, and gas we have being blown up through the center here. Now, another thing to note is this liquid is volatile. That is important for later. So what we know from that is that there actually is mass transfer happening between the gas and the liquid at that liquid interface. With that, we are going to need to find the mass transfer coefficient of that mass transfer that is occurring at the interface. So to do that, we're going to need some experimental data, but before we can do that, we're going to perform a dimensional analysis. To do that, we're going to need some dimensionless groups. We're going to be using the Sherwood number, which will be represented as SH. We're going to be using the Reynolds number, which will be used as RE. And then we're going to be using the Schmidt number, which will be as SC. So to start us off, we're going to have to find the units and the variables that are going to be used in this problem. We already established that we're looking for the mass transfer coefficient. We're also going to have velocity, because there are moving parts in this. We're going to have density. There's a difference in the densities of the liquid and the gas. We're going to have viscosity. We're working with the liquid here. We're also going to want that diffusion coefficient between the two. And we're going to have the diameter of the pipe as well. Now we're going to need standard units for all of these. The units we're going to use are kilograms, we're going to use meters for length, and we're going to use seconds for time. So we have the mass, length, and time. But now we need to establish where all these stand. Are they kilograms per meters per second? Where are they all at? So for mass transfer coefficient, we know that that is meters per second. Therefore, we're going to have meters here. Second is going to be -1 since it's at the denominator. And we don't have kilograms anywhere in this at all, so that'll just be 0. For velocity, it's the same story. It's 0, 1, -1. It's meters per second. For density, it's a little different. Density is kilograms per meters cubed. So we're going to want 1 for kilograms, as that's on the numerator, but we're going to have -3 for the meters, because it's meters cubed on the denominator. So it's kilograms per meters cubed. Time isn't a variable here. We don't have to worry about that there. For viscosity is kilograms per meters times seconds, or kilograms per meter per second. So we're going to have it as kilograms on the numerator, and on the denominator we're going to have meters and seconds. For the diffusion coefficient, that one is meters squared over seconds. So again, 0, 2 meters squared over seconds. So seconds is at -1. And the diameter, that's just a length. There's no meters, there's no seconds. It's just, there's no kilograms, there's no seconds. It's just the meters. So with that, we're actually going to want to find the number of dimensional screws involved. To do that, we're going to be using the number of variables that we have. We're going to subtract that by the rank. I'm going to use this in a different color just so you can see a little bit better. So we have n as the number of variables that we're using minus the rank is equal to the number of dimensional screws involved. We already have n because we know that we have 6 variables up here. So n is equal to 6. But we don't know the rank. To find the rank, we're actually going to have to jump over to Python right now. So as mentioned before, we're going to be needing to find the amount of dimensionless groups that we're working with. And to do that, we're going to have to find the rank first. With that, there's actually a line of code that we can use where we're going to have to first import numpy and then p. And we're going to use the linear algebra matrix function under numpy. and it'll also give us the rank that we need. So we're finding the rank, and with the amount of variables that we have subtracting by the rank, we will find how many dimensionless groups we're working with. And with that, we're going to also need the variables for this. We're going to be using from that chart the variables and the units that we had. We drew that chart out on the board, and we're going to use that horizontally. So for an example, we're going to have 0, 0, 1, 1, 0, 0, and those are the values of all the kilogram units for each variable. For an example, this first one is for that mass transfer coefficient, and so on and so forth. Next, we're going to be using the variables for meters, again, horizontally. 1, 1, -3, -1, 2, 1. And lastly, we're going to be doing the seconds. -1, -1, 0, -1, -1, 0. And with that, it gives us the rank of 3. So now that we have the rank, we actually can continue solving this problem. We know that the rank now is 3, which will allow us to solve this problem right here. We again know that there are 6 variables minus the rank 3, which gives us 3 dimensionless groups. This is great. We can work with this now, and to work further, we're going to be using the Buckingham Pi method to solve for those dimensionless groups. And we're going to use that because it'll make the problem easier to work with, and we can also then plot those dimensionless groups. But to start with that, we're going to have to establish, and at least this top part right here, not the whole thing, we're going to have to establish these dimensionless groups in 3 expressions. We're going to be using pi 1, pi 2, and pi 3. This is how I write pi. I apologize. I've just done it my entire life like that for some reason. But that is pi. That's how it looks like. But we're also going to have to find a core group from these variables. We're going to be using density, the diffusion coefficient, and diameter as part of our core groups, and the rest of these will be variables for each expression. So we can go ahead and erase all this down here and all that. And I'm actually going to set it up at the bottom here just so that we're aware later on what pi 1 equals, what pi 2 will equal, and what pi 3 will equal. But we're not going to worry about that right now. Well, we are. We're going to be solving for it, but we're just going to leave those to the side. That's just for us to have that visual representation for as we're solving it. We're going to start with pi 1. So pi 1, again, we have our core group as the density, the diffusion coefficient, and the diameter. So we have pi 1 is equal to, again, that core group, the diffusion coefficient, density, and the diameter. But we're going to add another variable to this. We're going to have that mass transfer coefficient as our variable. But we're going to want to have coefficients to this. So we're going to have it that this is A, B, and C. Because we're going to use those, we're going to solve for those, and find a way to make this all equal 0. Or at least we're going to make the the units equal to 0, because we want to make these dimensionless groups. So we're going to write out all the dimensions for this so that we can see how it works. We know that this is meters squared per second. And that is to the power of A. Density is kilograms over meters cubed. that's to B. Diameter, that's just meters, that's to C. And that mass transfer coefficient doesn't change at all, but it is meters per second. But there is no exponent to that, it's always going to be meters per second in this. So with that, we're going to need to solve for A, B, and C, which I'm also going to write down here so we can see it easier. And those are going to be numbers that we're going to have this to the power of so that we can make it that all of these cancel out to have it that it is 0. That was probably a little bit wrong right there. But so that those are equal to 0. So we're going to start off by getting rid of an easy one. This is the only place that we have kilograms available. And because of that, there's really no way to get rid of it by mixing it in with any other variable. So we're actually just going to make that B equal 0. Very simple. That's how we get rid of the kilograms. We can't do that with everything, sadly, though. I would wish, but it's not that easy. So now we are only left with meters and seconds to work with. We're going to solve for A and C, and we're going to first start off by writing out the units for meters. And the way we're going to do it is there's 2 meters here, or it's meters squared, but it's to the power of 2. So we're going to write that as 2A. Down here, we're not worried about that, that's all 0. We have right there 1, but it's 1C, so it's plus C. But we're also counting this. There is no exponent to it though, so it's just plus 1. And that must equal 0, because again, we're trying to cancel out all the units. There shouldn't be any meters once all of these are multiplied together. There shouldn't be any unit of that. But we have 2 variables there, we can't solve for it, so we're going to move on to seconds, where here we have seconds as negative A, it's negative 1 times that A. We don't have anything here, don't even need to worry about it. The only other place we have it is with that coefficient, that mass transfer coefficient, so we'll have that as minus 1, and again, that must equal 0. Because of that, we can see that A has to equal negative 1. That's great for up here, because now we can go ahead and erase that A there, that 2A, and we know that since A is negative 1, that's going to just be negative 2. Now we have one variable here, we can solve for that and find that C must equal 1. This is great for us to work with, because now I'm going to go ahead and erase this, and we can have that changed up there. So we know that the A is negative 1, the B is 0, and the C is 1. So we can actually go ahead and rewrite this as equal to that diameter times that mass transfer coefficient all over that diffusion coefficient. And there we go. That gives us for this first one, for pi 1, so I'm actually going to rewrite it as mass transfer coefficient times the diameter all over that diffusion coefficient. And now, next we're going to move on to pi 2, but this one's actually a lot easier, because we know that the units for Kc, the mass transfer coefficient, is equal, I'm going to go ahead and erase this top part, is equal to meters per second. Well, while solving the problem, that's what really matters, is that meters per second. And we know that meters per second is also equal to the velocity. Not saying that these two are equal to each other, but the units are the same. Because of that, pi 2 is really just going to be the same thing as pi 1. We don't have to worry about doing the math there. It's going to give us the same solution, except instead of that mass transfer coefficient, it's going to be velocity. So we have velocity times the diameter over that diffusion coefficient. And then we can go ahead and erase this. But we're still left with pi 3. Pi 3, we're going to have to work with a little bit more. So with pi 3, our variable is going to be viscosity. So we have that as, we still have our core group, and for pi 2, again, we're going to have the variables there when we're writing it out as that diffusion coefficient, density, and diameter. Instead of A, B, and C, because they're going to be different, it would have been D, E, and F. But again, we've already solved for that because we know that the velocity is the same as that mass transfer coefficient in terms of units. I'm saying that because we're going to change this up to and have the variables for that be, we're still having that same core group, but now instead of A, B, C, or D, E, F, we're going to have G, H, and I. And our variable that we're going to have next to it is going to be viscosity. With that, we can now solve for this. And again, we're going to put the variables. We know that this one is meters squared over seconds, and that is to the power of G. We know that the density is kilograms per meters cubed, power of H. And diameter is just meters. And viscosity, the units for that is kilograms over meters times seconds, or kilograms per meters per second. With that, we can't just simply cancel out those kilograms anymore. Sadly, I wish it would have been that easy again, but we can again work with that. It shouldn't be too hard because once we do kilograms, we know that we have this as 1h, so h plus 1 has to equal 0, so we know that that h has to be negative 1. I'm going to go ahead and rewrite this bottom part. So that h must equal negative 1 there. It was a bit easier to solve. Next, we're going to work with the meters. So with meters, we have it as 2g, and we have here, we already know that that is negative 1, so we're going to have that as negative 3, or sorry, negative 3h, which would make it positive 3, and then we're going to have this as plus I, and we're going to then subtract another 1 over there. And that must all equal to 0. We can't really solve for that because again we have two variables, but we can go ahead and work with seconds for now, where we have that as negative g, and then the only other place we have seconds is right there, where we will have that as minus 1 equals 0, so we know from this that g must equal negative 1. And that's great because we can push that right up there. Since g is equal to negative 1, we can change that to negative 2. Negative 2 plus 3 minus 1. We know that I is equal to 0 in that, which is very interesting for us. With that, with these, we can now rewrite that. I'm going to write it down here as that diffusion coefficient to the power of negative 1 times the density to the power of negative 1. This just goes away, and then it's times the viscosity to the power of 1 there. But we're going to go ahead and change that there, and we're going to make that, rewrite it as viscosity over that diffusion coefficient times the density. Now with this, we have found a bunch of dimensionless groups. We found these three dimensionless groups, and we're going to go ahead and give them names now. The pi1, which is the mass transfer coefficient times the diameter over the diffusion coefficient, is actually going to be called the Sherwood number. Pi2, which is the velocity times the diameter over the diffusion coefficient, is called the Pecklid number. The Pecklid number, not Pecklid. Which we'll write as that. And pi3, which is that viscosity over the diffusion coefficient times the density, all on the bottom there, is called the Schmidt number. These have names to them all. The issue is what we were looking for is the Sherwood, the Schmidt, and the Reynolds number. We have the Pecklid number instead. But if you look at these two, you can actually see we already do have the Reynolds number between these two. All the Reynolds number is just pi2 over pi3, which we can see that as velocity times the diameter all over that diffusion coefficient, and then all of that over viscosity over that. And with that, we can actually see cancel this out, this moves up to the top. So we get that it is the velocity times the diameter times density all over the viscosity. And that is equal to the Reynolds number. And that all that is just the pi2 over that pi3.